In today's class, we'll study what is magnetic flux density. So far, we have studied about H, which is magnetic field intensity, and we have seen what is Biot-Savart's law, its applications, as well as the same equipments when it comes to Ampere circuits law, how we are deriving, like for an infinite sheet, as well as spherical conductor. So all these things we have seen. Okay, so some more numerical problems we'll be doing once we go ahead in the module 3. So now we'll see what is the relationship between magnetic flux density and magnetic field intensity, as well as what is vector and scalar potential. Okay, so these things are mentioned in your syllabus. So let's see what is. So magnetic flux density, what does that mean? So magnetic flux density and all, I think you might have studied in your lower classes. So magnetic flux density is denoted by B. So it is denoted by B and is related to magnetic field intensity. B is equal to mu0 into mu r into H, and the unit is Weber per meter square, or we also call it Tesla. So the unit of magnetic flux density B is mu0 into mu r into H, and the unit is Weber per meter square, or Tesla we call it. And we know that magnetic flux phi is equal to integral over S B dot ds. I think this equation you are studying from your 12th standard physics. Flux is equal to integral B dot ds. So maybe you might have studied B dot ds. Like you might have studied that. And what is mu r here? Mu r is the relative permeability. So once you study one equation means you should know what are the terms in that, and mu0 is the permeability of free space. Mu0 is the permeability of free space, and it is given by 4 pi into 10 raised to minus 7 Henry per meter. And phi is the magnetic flux in Weber. Phi is the magnetic flux, and that unit is Weber. So all these basic things you should know. So you know one equation, what are the terms and all, everything you know. So what does that? So we in module 2 we have studied about electric field intensity. So what difference it has from magnetic flux density? So it is like, unlike electric flux lines, magnetic flux lines are always closed upon themselves. Like if you have a magnet here, and this is the north pole and this is south pole. So magnetic flux lines will be going from north pole to south pole, and inside it will be from south pole to north pole. So I remember the studying in 12th standard. So where I think 10th, 11th and 12th, first of all, when we are studying magnetic field, or I think our teacher will come with a magnet and a paper, and he will put some magnets over that, and he will show how this field is making. So in my school, from my school, I am remembering these things. So I think you might have also studied very first time when we are studying magnetic field. So the same field here. So magnetic field will be from north pole to south pole, right? It is not like electric flux coming out, not like that. So it will be closed upon themselves. So that's why we say integral B dot ds is equal to 0 over a surface, because it's not like the electric flux lines. Magnetic flux lines are always closed upon themselves, and we can also say that isolated charges does not exist. Like there should be a north and south, like that only it will be existing. Isolated charges does not exist. Like you have north and south here. So from south to north it will go. Similarly, same way. So it will be like they will not exist isolated. So these are just the theoretical parts that you should know. So from the divergence theorem, so now we have the application of divergence theorem. So what does divergence theorem say? So divergence theorem say integral B dot ds is equal to integral over V del dot B dV, and you know that for a closed surface, integral B dot ds is equal to 0. From that you will get del dot B is equal to 0. So we can say that the magnetic flux lines are always continuous, and the del dot B is equal to 0, and this is one of Maxwell's equation. So these are the basic things that you should know with regard to magnetic flux density. So is it clear? So now we will see the 4 equations of Maxwell, which we already studied in differential form as well as integral form. And then we will be studying the modified form. Towards the end of this module, we will be studying the modified form of Maxwell, where we will get the conduction current. We will see all those things. So now just summarize. So we have the differential form. Differential, or we say it is the point form. And then we have the integral form. And then we will give some remark also. What does that equation signify, and all these things we will see now. So we can say it like, equation will be, this equation we have studied, del dot D is equal to rho V. This equation we have studied. Or we can say that integral over D dot ds is equal to integral over V rho V dV. So what does that, what was this law? How equation law do you remember? Del dot D is equal to rho V, integral D dot ds is equal to rho V dV. How we got that?
Gauss law.
Yes, very good. So we got it from the Gauss law. Then we just now we studied that del dot B is equal to 0. That is integral B dot ds is equal to 0. So what does that say? I explained to you now. Magnetic monopoles does not, I didn't use the word monopole. So what? So I think you might have studied all these things. So isolated magnetic poles does not exist. That means magnetic monopoles does not exist. So that is your equation. You know, what we are studying is non-existence of magnetic monopoles. Non-existence of magnetic monopoles. And then another equation we have studied, del cross E equal to 0. That is integral E dot dl is equal to 0. Very important. It can come as a theory question. That is conservative nature. We have studied integral D. That is electric field is conservative. So that is this is from the second module. So conservative nature of electrostatic field. Then another equation we have studied, del cross H is equal to J. I think in the last class we studied del cross H is equal to J. That is integral over L H dot dl is equal to integral over S J dot ds. And what was that law? From which law we got that? Ampere's law or Ampere circuit's law. So these are the these 4 things you should know. May not be KTU examination point of view. They may not ask you what are the 4 equations and like that. But if you electromagnetic theory, if you're studying, means these things you know with the significance. So once you know the significance, you know the behind story. How we reached here, what is Gauss law, what is, so all the conservative nature, all these things you know, the behind story you know. So this is the most basic understanding. Okay. So I'm just sharing that with you. Now we'll move on to the next topic. The next topic that we need to see is scalar magnetic potential. So this can come as a theory question, as well as they can ask you simple numerical problems. So because this is all based on some simple equations. So we know that in electrostatics, given a charge configuration. So in electrostatic, if a charge configuration is given, we may first find the potential, and then from it, the electric field intensity can be found, right? So in electrostatics, if a charge configuration is given, so you know the equation for all these things. If a charge configuration is given, then we may find potential from that, and then electric field intensity. right? So what is the equation for that? You know the equation. The equation is E is equal to minus del V. So likewise, we used to find out. And similarly, when it comes to a magnetic field intensity, we know that del cross H is equal to J. We have studied in the last class, like del cross H is equal to is equal to J. Del cross H is equal to J. So this is for electric field intensity. Similarly, for magnetic field intensity, we can write a similar equation, that is H is equal to minus del Vm, where Vm is the scalar magnetic potential. So I'm just comparing and giving you scalar magnetic potential. So now so after that we will be studying vector magnetic potential also. That also we will see. So one by one we will see. So you are familiar with this equation that electric field intensity is equal to minus del V. Similarly, for magnetic field intensity, we can write like H is equal to minus del dot Vm, where Vm is the scalar magnetic potential. And also we have studied in the first class, very first class, we have studied two identities. I mean, in module 1, you might have studied two identities. That is del cross del V is equal to 0. Similarly, del dot del cross A is equal to 0. You might have studied, where V is a scalar and A was a vector, right? So this was curl of gradient of scalar. I'm just rewinding. Curl of gradient of scalar, and this was divergence of curl of a vector. So we have this equation, right? Del cross del V is equal to 0. And similarly, we have H is equal to minus del Vm. And also we have del cross H is equal to J. And this del cross H can be equal to 0 if the current density is 0. If J is equal to 0, then del cross H will be equal to 0. So all these things we can say. So combining all the three equations, we can write. So del cross del Vm is equal to 0. We already know. We have derived it in the first module. So from that we can write del cross del Vm is equal to 0 and H is equal to minus del dot Vm. So H is the magnetic field intensity and Vm is the scalar magnetic potential. Therefore, del cross minus H is equal to 0, right? Del cross minus H is equal to 0. So now what, and also we know that del cross H is equal to J. So what does that mean? Comparing these two equations, that is this equation and this equation, we can say that scalar magnetic potential is defined for J equal to 0. So what is the conclusion? H is equal to minus del Vm if J equal to 0, and the potential also we can write. If you consider from A to B, what is the potential if you are considering from A to B? It will be B to, minus of B to A integral H dot dl. So what is integral H dot dl and all we have already seen. So if a question comes like what is the scalar in terms of what is scalar magnetic potential means, this is what you should write and explain. Okay, that is current density is equal to 0. That is permanent magnet or the current carrying element is very small. Current density equal to 0. What does that mean? If J is equal to 0, physical meaning എന്താണ്? അതൊരു permanent magnet ആണ്, അല്ലെങ്കിൽ അതിന്റെ current carrying element എന്ന് പറയുന്നത് വളരെ ചെറുതാണ്. That's why it does not have a current density ഇല്ല എന്ന് പറഞ്ഞാൽ what does that mean? If you have a doubt, means that is a physical meaning for that. So for a specific path, if you are taking means Vm is equal to minus integral b to a h dot dl. So that is from this is actually from the ampere circuits law. So we have combined all these things. So this is the significance of scalar magnetic potential. So scalar magnetic potential is defined at J equal to 0. That is del cross del Vm is equal to 0. So how we are arriving there, you should know. Del dot H is equal to minus del Vm. So from that we also know that del cross del Vm, because for del cross del Vm to be equal to 0, Vm should be a scalar, and we are studying about scalar magnetic field only. So del cross del Vm equal to 0, it's fine. Now this del Vm we replaced by using H. Then we got del cross minus H is equal to 0. And also we know that del cross H is equal to J. That is from the Ampere's law, we know that. So then we realize that scalar magnetic potential, if that needs to be defined, then J should be equal to 0. So what does that mean? J equal to 0. J equal to 0 means the current density is 0. That is, current carrying element is very small. Current carrying element very small. So that's how we conclude. So if it's for a specific path, means it should be from H dot dl. So we know that del dot B is equal to 0. We know that, and also we know that B is equal to mu into H. Then del dot mu H is equal to 0. Then mu, if you are taking out, it will become del dot H is equal to 0. So you know that H is equal to minus del Vm. So it will become mu into del dot minus del Vm is equal to 0. Then we can say that del square Vm is equal to 0 at J equal to 0. So what is the conclusion? We can say that the scalar magnetic potential, satisfies Laplace's equation. So if you get a question for 7 to 8 marks, what is magnetic flux density? Explain scalar magnetic potential. So you can write all these things. Okay. So not just if you write only these equations and all, means it will be very small answer. So I have seen that 1 minute. Now we will study what is vector magnetic field. So we have seen what is a scalar magnetic field. When we studied scalar magnetic field, del cross del V was becoming 0. So when it comes to vector magnetic field, del dot del cross A, that is divergence of curl of a vector. We will see. So before moving on to the equation, we'll see some theoretical aspects behind that. Why we are studying vector magnetic field. So vector magnetic field, it is denoted by A. Vector magnetic potential, actually, it is denoted by A, and the unit is Weber per meter. And the applications means it can be used for the study of radiations from antenna, radiation leakage from transmission lines. So I'll give you some applications also. So if you are reading the textbook, Sadiku or you Bakshi, if you are reading, then these things are mentioned there. So radiations from antenna. So here we will be studying. The applications is radiation from antenna. So if an 8-mark question comes and is asking for vector magnetic potential, you write all the equation, write application also. So then radiation leakage from transmission line. Leakage from transmission line. Then microwave ovens, etc. All these things have magnetic vector potential applications. So you know that, so it is denoted by A, and you know that del dot del cross A is equal to 0, where A is the vector magnetic potential. That is del dot del cross A. And you also know that del dot B is equal to 0. Then from that we can write del cross A is equal to B. So what does that mean? Curl of the vector magnetic field is the flux density. So what does that say? Curl of the vector magnetic potential is flux density, and unit is Weber per meter. Then also we know that it's all about equations, okay? Also we know that B is equal to mu 0 into H. Then we can write del cross A is equal to B to us. That B we can replace by mu 0 into H. Then from there H is equal to 1 by mu 0 into del cross A. That is one equation. Then also we can write del cross A is equal to mu 0 into J. Okay, or you can write J is equal to del cross A divided by mu 0. So from that we can write del dot A minus del square A is equal to mu 0 J. Then so the current density can be calculated if we have the vector magnetic potential. Current density J can be calculated if we know the vector magnetic potential. So one step I missed here, I will show you. We know that del cross H is equal to J. Then H is equal to B by mu 0, right? From that you get del cross B by mu 0 is equal to J. So here we substitute this concept, this equation we substitute here, and then we get J equal to del cross A by mu 0. So from there we get del cross A is equal to mu 0 into J. Okay, then we can write if del dot A, if it is taken to be 0, then J is equal to 1 by mu 0 into del cross A, that is del square A is equal to minus mu naught J. So certain equations that we will get. So J is equal to 1 by mu 0 into del cross A. And if you are not neglecting this del dot A means, then J will be equal to 1 by mu 0 into del dot A minus del square A. So this is how we conclude. I will just explain once again. So we know that del dot del cross A is equal to 0. That is divergence of curl of a vector is equal to 0, where A is a vector. Then del dot B is equal to 0. From that you know del cross A is equal to B. Already and also B is equal to mu naught H. From that we got del cross A is equal to mu naught H. Now we are worried about H. So for H we brought an equation del cross H is equal to J and H is equal to B by mu naught. So del cross B by mu naught is equal to J. From this equation we got H is equal to 1 by mu naught and del cross A, and that we substitute here. Then del cross A by mu naught is equal to J. Then finally we get del cross A is equal to mu naught into J. Then we can also write del dot, that if this term is equal to 0 means del cross A by mu naught is equal to J. Then del square A is equal to minus mu naught J. So what is the conclusion? So current density can be calculated if we have the vector magnetic potential. So J can be calculated. The current density J can be calculated if we have A. So that is the conclusion that we are taking from vector magnetic potential. So we have a question. So that is with respect to vector magnetic field. You should identify that it is a vector magnetic field from the unit Weber per meter square or from the symbol. So in cylindrical coordinates, we have given a vector magnetic field A in a certain region of free space. So A is 50 r square into A is that in a certain region of free space. So there we need to find the magnetic field intensity, magnetic flux density, current density, and using J, we need to find the total current I crossing the surface. So maybe you can do integral J dot ds. I is equal to the total current you will get. So we'll see one by one what is to be done. So how how we solve these things we'll see now. So we are given A is equal to 50 into r square into AZ. And you know that magnetic field B, direct, nothing to do. Magnetic field B is equal to del cross A. So you do del cross A. So del cross A. But what is important to do del cross A? You should know the formula for curl in cylindrical coordinates. Module 1. So del cross A is 1 by R AR RA phi AZ dou by dou R dou by dou phi dou by dou Z, and then here R and phi is 0, then here it's only 50 r square, or what is it? A is 50 r square, and now you do the cross product del cross A. So that is equal to 1 by R into what? So now we will do del cross A. So it will be 1 by R into AR into dou by dou phi of 50 r square minus R into dou by dou R of 50 r square into A phi. Just del cross A, whichever way you want, you can do. 1 by R is equal to minus R into 100 R. 100 R means 50 into 2 R. I'm directly writing 100 R into A phi. So this one will be 0. Here only we are changing. With respect to phi, it will be 0 into A phi. So that is equal to minus 100 R A phi Weber per
R square.
minus 100 R square illa. Here R would cut out. 1 by R would law. So it is Weber per meter square. Because we have what we have found out del cross A del cross A B magnetic flux density. So that is Weber per meter square. So now we need to find out H, magnetic field intensity. You know how to find it because you know the equation B is equal to mu 0 into mu R into H. So if mu R is not given, take it as 1. So H is equal to B by mu 0 into mu R is equal to minus 100 by mu naught into R into A phi ampere per meter. And also we know that now we need to find out J. So for J, you need not go for integral B dot ds and all. J is equal to del cross H. J is equal to del cross H. That also we know already. So same formula you can use here for the cross product. Same formula. So that is equal to 1 by R into AR R A phi AZ and dou by dou R dou by dou phi, dou by dou z, then 0. Then what is the coefficient? How it will come? It will come like R into 100 divided by mu naught into R, and that other one will be 0. So നമുക്ക് B കിട്ടിയതിന്റെ കൂടെ mu naught കൂടെ നമ്മൾ divided by mu naught കൊണ്ടുവരിക. Then we will get H. So that is equal to 1 by R into dou by dou R of, കാരണം ഇവിടെ ഒരു ഇൻറ്റു ആർ നമ്മുടെ ഫോർമുലയിൽ ഉള്ളതാണ്. ഒരു ആർ എന്ന് പറയുന്നത് ഇറ്റ്സ് ഓൾറെഡി ദർ ഇൻ ആ ഫോർമുല. പ്രീവിയസ് സ്റ്റെപ്പ് എഴുതിയപ്പോൾ അവിടുത്തെ കോഎഫിഷ്യന്റ് 0 ആയിരുന്നുകൊണ്ട് we didn't mind that. പക്ഷെ ഇവിടെ വന്നപ്പോൾ there is an extra r there, so don't get confused. So 1 by r into dou by dou r of minus 100 r square by mu naught into az minus dou by dou z. നമ്മൾ എങ്ങനെയാ ചെയ്യാം? We'll look like this and we'll cross multiply. So just do that. Minus 100 r square by mu naught into ar. So if anybody is having any difficulty in doing these mathematical operations, integration, change of limits, cross product, dot product and all, just message me personally. I will try to help you. Because in the class, I cannot explain all those things. That will take a lot of time. And many of the students know these things already very well. So it will be a waste of time for them also. So if you have any difficulty, you can ask me personally. If there are more students, means I can give you a live session also. We will just solve all these things. So we can do like that. So we calculate J. So del cross H is equal to J. So we have done del cross H here and you got J. Now what we need to find is a total current. So this question was actually asked in one of the previous university for your S6 electromagnetics. The total current I crossing the surface, the total current I crossing the surface, and what will be that? I is equal to integral over S J dot ds. So now we need the limits. So wherever the current is flowing, we need the limit. So it will be integral over S J dot ds is equal to integral pi is equal to 0 to 2 pi integral R is equal to 0 to 1 minus 200 by mu naught into AZ, and ds you know. Cylindrical surface ds we have studied in first module. This R dr d phi AZ. So minus 200 by mu naught AZ into R dr d phi AZ. So now it's all about integration. Minus 200 by mu naught R square by 2, 0 to 1, 0 to 2 pi. So it will be the final answer and write directly. So it is minus 500 mega ampere. Maybe 10 raised to 6 it will come. Because this mu naught value also we need to substitute. So from there you will get 10 raised to and all. So what you are finally getting is minus 500 mega ampere. So what was the question about? The question they were asking, they gave us a vector magnetic field and then they asked us to find HBJ. So all the equations directly you know. So only thing is that you should be good in mathematics. So cross product, integration, giving the limits, giving the upper limit, lower limit, solving that. So all these things are very important here. So I hope this problem is clear for you.